Hello, everyone, and welcome to Water Activity 101, Mastering the Basics. Today's presentation will be 20 minutes, followed by 10 minutes of Q&A with Mary Galloway, application scientist here at Meter Food Research Lab. If you have a question for Mary Galloway, type it into the questions pane at any time during the webinar, and we'll be keeping track of these to answer during the Q&A. So please don't be shy and submit those questions. We'll also be sending out a link to the on-demand webinar, as well as the slides for you to review as soon as they're available. So without further ado, I'll hand the microphone to Mary.
Good morning, everyone. Thank you for joining us here today for Water Activity 101, Mastering the Basics. I'm Mary Galloway, and I'm going to get right to it. So today we are going to cover what is water activity, what is the difference from moisture content, how does water activity control microbial growth, and how can water activity help overcome moisture-related challenges. Have you ever wondered how you can have a nice tender raisin and a crispy bran flake, or a snack cake that can maintain the texture of all of its components? And the same with the cheese-filled cracker. How can you avoid caking and clumping issues with ingredients, or determine if your product will be susceptible to spoilage? All of these examples are controlled by water activity. If you understand how water activity works, you'll be able to develop products that are stable and desirable to the consumer and can predict and prevent potential problems. Let's start with fundamentals of thermodynamics. Energy is a driving force for processes to happen. More energy equals more processes and more things can happen, meaning work. Work can be done here. In this case, we're talking about mechanical, thermal, chemical, etc. We also know that a higher energy state wants to become a lower energy state to become more stable. So how does this relate to water activity? Well, water activity is a principle of thermodynamics and follows the same rules. Water activity, with the A sub W, is the measure of energy status of water in a system. It is denoted as A for activity, sub W for the water. And if we have a higher activity, that also equals more energy, and the water can do more. And the work here is microbial growth, moisture migration, chemical and physical reactions. Also, differences in water activity will dictate how moisture will move. This is in terms of energy, not concentration. Higher water activity will go to a lower water activity. That means that water activity at that means that the water at a higher water activity has more energy than the water at a lower water activity. How is it going to lower its energy status to become more stable? Migrate to a lower water activity. All right. When we're talking about energy systems, we can adapt the Gibbs free energy equation to determine activity of the water in a system at a given temperature. If we want to determine the energy of water in a system, it would be equal to the energy of pure water plus the gas constant, which is R here, times the temperature, and then the natural log of fugacity. Now, since mu sub A, which is this first term here, which is the chemical potential of a pure substance. So for our case, this would be pure water. R, the gas constant, is a constant, and T is also temperature, is held constant as well. The only thing that's really dependent here to determine the energy of the water is this term, this last term here, called fugacity. So what is fugacity? It is the escaping tendency of a material. What vapor can escape out of the sample? How can we measure fugacity? It can be measured by partial pressures or vapor pressure of water above a sample at a specific temperature divided by the vapor pressure of pure water at the same temperature. And relative vapor pressure, or sometimes it's termed partial vapor pressure, is exactly water activity. If we can determine the partial vapor pressure of a sample, we can calculate the water activity. So here is this little diagram to help illustrate what is vapor pressure. We have a sample of food in a container on the left. Water molecules are escaping out of that sample. We can see it above there in that headspace. those molecules will produce a specific pressure inside a sealed container. This pressure is compared to the pressure produced by pure water, as demonstrated in the container on the right. Since this is a ratio between two pressures, water activity is unitless and on a scale of 0, no energy, to 1, the same energy as pure water. It is important to point out that pressure needs to be allowed to equilibrate so that there's no net change here. So we have water molecules going up into the headspace and then coming back down into the food product. But overall, there's no net change. So that's an equilibrium. And the temperature and pressure need to be constant. Water activity at 25 C will be different than the water activity at 35 C, and generally it will be higher. So if you're taking samples, doing water activity measurements, you need to know that if you take a reading at 25 C one day and then the next day you have something where you're taking it at a different temperature, they will not be the same water activity because it is dependent on temperature being constant. All right, so let's discuss moisture content. So it is a qualitative measure of the amount of water. Before we were talking about the energy status of water, moisture content is the straight amount of water. We have two primary methods here. One is loss on drying. So what you would do is you would take the wet weight of the sample and you'd minus the dry weight from that. And then, depending on what basis you are going to use, you would divide by either the dry weight for dry basis or wet weight for wet basis. Now, it's important that you know which basis you're going for because each of those will give a different answer because you are dividing by different weights. Unfortunately, the basis is not often noted very much in loss on drying. It's just a % moisture content. There's a times 100 at the end there, and that's how you get it into 100%. But here we always use wet basis because dry basis can actually give you a negative moisture content, which, as we all know, is not real. That cannot happen. Another primary method is titration, which is also known as the Carl Fisher. This is a chemical reaction where you react water, iodine, and some solvents. The reaction continues until all of the water is used up, at which point the electrical conductivity changes in the solution. The conductivity is measured and then used to calculate the % moisture content. There are potential problems with this method, though. One being that all of the water needs to be solubilized and available to react, which can be difficult if your product is not a liquid. And you need to know which solvent to use to be able to do that as well. So there's not really one size fits all for the solvents. There's a main one that they have that does a lot, but that's not always going to be effective for every sample. And there also can be side reactions happening with the solvents, among other things, that can affect that measurement. For any method for determining moisture content, there is no standard. There's nothing that has an intrinsic moisture content of X to which we can compare. We can get an answer for moisture content, but we don't know if it's right. So comparing water activity and moisture content here. Water activity is the energy of the water in a system. For moisture content, we're talking about the amount. Water activity is a qualitative measurement, meaning it is defined by the product itself and the interactions of the water inside the product that determine what the water activity is. Moisture content is qualitative. You are going to get a number. Water activity is a driving force based on the principles of thermodynamics. Moisture content is not a driving force. It does affect texture, but not a driving force for reactions and changes in a product. With water activity, there are known standards. You can make a saturated slurry. Greenspan has a whole chart of them. And if you make them correctly, they will produce a specific water activity that can be determined theoretically and then proven empirically. We've been able to take that one step further and make unsaturated salt solutions that have a known water activity as well. They're also based on theoretical equations, concentrations, and density, but are less susceptible to issues that make saturated salt slurries difficult if you've ever tried to make one and kind of finesse them so that they get what you, the level you want, then you can know that it can be a little tricky. For moisture content, there is no standard, like I had mentioned before. You get an answer, but you don't know if it's the correct answer. You can strive for precision, how repeatable your answer is. Otherwise, you don't actually know. Also, other substances besides water can be evaporated off when you do like on loss on drying. Alcohols and other volatiles can be driven off, and that would increase your moisture content. For water activity, we already discussed that it's unitless because it's a ratio of vapor pressures with units canceling out. And for also for loss on drying, which is the most common method here, you need to define either wet or dry basis before you begin. All right, we're gonna have a little demonstration here. So we're gonna compare honey versus a nice crunchy cookie. How would you compare the moisture content between the two? Would you expect the moisture content of the honey to be much higher than the cookie? I would say yes, right? We would say, okay, well, the honey is nice liquid and the cookie is nice and crunchy, and you would be right. So we have moisture content of the honey is around 18%, and for the cookie, it's only 5%. Now, what would you think about the water activity? Do you think they are the same or different? Let's find out. In this case, the water activities of the honey and the cookie are exactly the same. Products have drastically different moisture contents, but the same water activity, and they are both shelf stable. All right, what would happen if I submerged the cookie in the honey for a week? Would the cookie become soft? What is the driving force in reactions, namely moisture migration? So we've talked about this. It's water activity, right? It's not moisture content. So nothing would happen because the energies or water activity are the same. Now, there are applications for both water activity and for moisture content. I want to briefly put up here a bit of a list, but I'm not going to go, read through it right now. And you're welcome to review the list in the future. The slides, as Brad spoke, will be made available to you. I will be focusing on the top 4 for water activity here, hopefully touching on number 5, which is controlling chemical reaction rates. For moisture content, I do want to say that it does affect texture. Think of the example with the honey and the cookie. Totally different textures, totally different moisture contents, right? But then the same water activity. You can use moisture content to increase or improve the texture depending on what kind of product you want. It can be used also to determine ingredient concentrations or nutritional content, which is important for labeling requirements. If you have a moisture content limit, like with pet food at 10%, you would need to determine the moisture content to know if you are in compliance. All right, so let's continue here. Now, I wanted to point out that there is a relationship between water activity and moisture content, but it is unique to each product and formulation. This graph shows some products that we have tested and the relationship between water activity and moisture content. They are all completely different. There is icing, there is cream filling in a cake, which sounds like the snack cake from the beginning of the webinar. All of these graphs have different shapes. There is this relationship between water activity and moisture content is actually a really important relationship to make. These are called moisture sorption isotherms and can be used to determine critical water activities. That's where the moisture sorption properties change, meaning that they physically change and can take up more moisture. And we can determine that where there is a change in the slope of the curve. Now, when these changes happen, we're going to start seeing changes in texture, and we're going to see also other changes that can happen. Right? You can also determine the effect of formulation by comparing the different respective isotherms from one formulation to the next. We can model dry ingredient mixing. So if you want to know what's going to be the outcome of mixing two ingredients, where is their water activity is going to end up, you can use isotherms to do that. We can also determine the effect of temperature abuse. If you have a product shipped out and stored in a hot truck hot truck or warehouse, what will happen to the product when it gets to the retailer? You can perform isotherms at different temperatures and predict what the effect will be. Isotherms also are essential for predicting shelf life. All right, so these are the applications that we're going to focus on now. And first up is microbial growth. All right, so microorganisms need water for growth, and they get that water from their surroundings. When an organism is surrounded by a lower water activity than its interior, it will experience osmotic stress. And we have over here example of a cell, and we can see in here that the water activity inside the cell is 0.95. And then outside of the cell, its surrounding environment here, the water activity is at 0.90. So we know from what we've learned about energy and water activities and how they want to go from high water activity or high energy to low water activity, low energy, know that the water inside the cell is going to want to move out. And when it does that, it is going to lose trigger pressure. And that is not a good state for the cell to be in. All right. So what is going to happen to the cell? Well, it's going to try to adapt. So it's going to try to overcome that difference by lowering its own internal water activity. So it's going to change metabolic process and try to introduce like amino acids, polyols, sugars, that kind of thing, whatever it takes so that it can try to reduce its internal water activity to match the environment on the outside. Now, if it can match, like in this example here now, it's lowered it by 0.2. If it can match what's in the environment, then it will start to grow. It will have enough water, enough energy to be able to start growing and reproduce. But what if it can't? As in this example here, it lowered itself to 0.93, but it's still not matching what's outside at 0.90. So what happens? Well, there is not enough energy for the cell to start growing and reproduce anymore. So it's going to go dormant. And how well a microbe can adapt and lower its water activity dictates what that water activity limit is. And in the 1950s, Dr. Scott showed that microorganisms have a limiting water activity level below which they will not grow, meaning that there is a specific water activity for each microorganism that will inhibit their growth, and they cannot grow in an environment below that limit. All right, so I have a chart here that focuses on bacteria. You can see here on the chart we have E. coli, some botulisms, salmonella, listeria, and each have a specific water activity limit in which they can grow. So if we look here for salmonella, it's 0.095. Listeria is 0.92. Down here in this highlighted portion, it says optimum conditions for pH, temperature, nutrients, and competing species. And what that means is that everything else is perfect, the ideal conditions for pH and temperature and nutrients, and there are no competing species for that bacteria to grow. Now, if any of these change, then they're not ideal. And actually what will happen is the water activity would have to be increased. So it can be, they can grow at a higher water activity than this limit, but they can never grow at a lower water activity than this limit. And it doesn't matter what matrix this is in. So if it's in a cookie or a powder or a pet food, if these are if these are present in those different matrices, it will not grow below that limit. Now, I need to point out that water activity is not a kill step or removal of the bacteria. It's a control step that prevents the growth of microorganisms. So it's safe but not sterile, so they're still there. If these foods were in presence of a higher water activity than what their limit is, they could grow. That is a potential problem. But if we're able to formulate so that we can keep our water activity low enough, then we won't have a problem. Now, I wanted to point out here one at the very bottom here, this aerobic staph bacteria. It has a minimum water activity of 8.6. Now, that means that everything above 8.6 and up here is what they consider potentially hazardous food. If these start growing, these can really make people sick and put them in the hospital. So those are deemed potentially hazardous. Now, everything below 8.5 is a limit where that cannot happen. All right, so here's another graph showing the entire water activity range for various organisms and when they can begin to grow. So here we have, besides the bacteria, also included are molds and yeast. It also shows some typical foods that are also found in the same water activity range as those. So you can kind of get an idea of what these are looking like. Now notice above 0.85, that's where we have the potentially hazardous foods. So there's a line there. We also have molds tend to have a lower water activity limits, but those involved in spoilage are at or above 0.7. Also notice that there is no growth for any microbe below 0.6. Hopefully some of these limits should sound familiar to you, and now you know why. If you are able to use this information, then you can produce products that will not be potentially hazardous if you have something above 0.85, or from 0.6 to 0.7, we know that no mold can grow for spoiling. All right, so I'd like to give a little bit of a case study here for the microbial growth. We're going to start with this example of moldy pecans. All right, so we have a grower who always dries his pecans to 4% moisture content. Not really sure knowing how dry is enough for the microbial growth. And historically, this has always been fine. He hasn't had a trouble with having this 4% as his moisture specification. After running an isotherm to determine the relationship between water activity and moisture content for the pecans, we find out that water activity of 0.68 relates to a 4% moisture content. And we know that water activity of 0.68 is below the microbial limit for growth, so it shouldn't happen. So if he's able to keep this here, then we can see that it's going to be fine, that they won't be able to mold. Well, they did mold. So what happened here? Well, we can see that unfortunately his moisture content measurement was only accurate to 0.5%. When the pecan measured 4%, it was actually probably closer to 4.5%. And the water activity exceeded the safe limit for mold, and that's how we can see this. This example is really about setting adequate quality specifications. By using moisture content as a quality spec, the pecans could be anywhere from 3.5 to 4.5 moisture content, and the grower would never know because he just isn't able to measure the differences there. But we know when we compare that to water activity, that's going to be a huge difference in water activity. So if his moisture content is from 3.5 to 4.5, we know that the pecans could either be susceptible to mold again, or they could be actually making less profit from a lower quality, harder nut, because if we're dropping the moisture content, we know that affects texture then. So it's lighter because it doesn't have as much moisture, and it's not as much harder nut. So I would think that would be a less quality nut to sell. Now, if they use water activity as their spec instead, they would know exactly where the pecans are at, and they'd be able to avoid either issue. So they could control exactly the quality of the pecan that they'd like. So they could keep the moisture content at 4% by using actually water activity to say, okay, our specification is going to be 6-8. So they can know how he's supposed to dry or and make process adjustments there. All right, so our next example is for caking and clumping. And I don't know if this is an issue you've ever had before, but it definitely happens. So here we have a dry soup manufacturer that processes a mix to 3% moisture content. And they receive in some new pepper, which also is at 3%, and they mix them together. So they mixed them together and then left them, and the entire batch clumped. So what happened? They're at the same moisture content. Well, we know that moisture content is not a driving force for things to happen. So let's look at the water activity. Well, when we do that, we find that the water activity for the soup mix was 0.28, but the water activity of the pepper was 0.69, which was above the critical water activity of the soup. So what happens when we have this discrepancy, this difference between water activities, we're going to see the high net moisture migration, and that's exactly what happened. So we have moisture migrated from the pepper into the soup, and now the soup mix has clumped. All right. If the manufacturer had measured the water activity when he got the pepper before adding it to the soup, they would have known that this would cause caking and clumping, because they would know that that's above this limit for the soup, and then they could have avoided that. Also, by tracking water activity of incoming ingredients, the manufacturer could monitor quality and consistency in their suppliers, and they could set an acceptance spec that would be below the critical water activity for the soup mix. So they could use this information in multiple ways, and then they would be able to save this product and be able to have consistency in their incoming ingredients. Let's talk a bit about product formulation. So here we have the isotherms for icing, cream filling, and cake. The example of our snack cake, at the beginning of the webinar. We see that they all have different relationships to water activity and moisture content. All those curves are completely a different shape. If we determine what we would like the snack cake to have a water activity of, and let's say as an example 0.7, as we're showing here in the graph, we can use that in our formulation of the individual ingredients. At a water activity of 0.7, if we follow that line that's going up here in the middle of the graph right here, all right, we can see that they all have very different moisture content. The icing is about 5%, the cream filling is close to 15%, and the cake is at 20%. And you can tell that they all have very different moisture contents, and in turn different textures when you take a bite of that snack cake. And each component is able to maintain their texture and moisture content because the water activity of all of them is the same. So we're not going to have any bleeding of moisture in from one to another. All right, here's another example of product formulation. We have a pet food manufacturer who produces to a moisture content of 6.5. Why? Because he knows that he's never had any trouble with that spec before. Everything is always safe. There's never been any spoilage problems. It's good, which is fine. And now we can see that if we continue, after reading the water activity, we find that at that moisture content, the product actually has a water activity of 0.4, which is well below any of the microbial limits that we've talked about in the past. But it's also very low. So with a maximum moisture content for pet food of 10%, which is where he could be, or they could be, could they safely increase their moisture content and water activity to increase their profit margin? Could they also improve their product? So there's nothing wrong with this product per se, but could they improve it? After considering the critical water activity for the pet food, a new water activity of 0.6 was set as an acceptable limit. And that takes a little bit of investigation to know doing some shelf life calculations and things like that to know where is a good acceptable limit, but it's completely doable. And you just need to be able to do the isotherm and develop that relationship between water activity and moisture content. So if we do that and we look at 0.6 as an acceptable limit for us for water activity, from that isotherm data, we can see that it corresponds with a moisture content of 9.5. Now, both of those values are within safety and regulatory limits. So that is a perfect spec to set, okay? Now, by increasing the water activity and the moisture content spec, they are able to reduce their raw ingredients costs. Now they would need less ingredients to produce the same amount of pet food. And they would be essentially replacing it with water, and water is very cheap. They could reduce electricity and heat because there's less time in the ovens, and the product is better because the moisture content is higher. It has more flavor, there's an improved texture as it's not as hard. So by understanding water activity, the manufacturer was able to consistently increase their profit without compromising quality or safety. And as a matter of fact, I think they've probably improved their quality of their product. So I wanted to point out this briefly, this chemical and biochemical stability chart. It's important to understand that water activity can influence the reaction rates of various types of chemical reactions that occur in food and pharmaceuticals. This is a graph that was developed years ago by Dr. Ted Labuza. And you can see that most of the reaction rates increase at water activities around 0.6 or so. And we can see some of the ones we've already discussed. We can see where bacteria lies, where yeast, where mold grows. But there's also some other things on here like enzymatic activity. Something that I wanted to point out was a little interesting is we have it's interesting of the browning reactions that peak around 0.6. And the reason those peak there and then fall off is that they start getting how can I say? I can't think of the right term. I apologize. There's more water in the matrix there, and so they get diluted. That's what I'm trying to say. So that's why the browning reactions peak there and then come down, because there starts to be a dilution effect. Also interesting to point out is lipid oxidation, and that one follows an unusual trend where it's high at low water activities, but it's also high again at higher water activities, where it's most stable is around 0.3 to 0.4, which is important for some products that have a lot of fat and oil in them, like a potato chip or something like that. So that's all I want to say about this one at this time. We have more information about these if you're interested. All right, in conclusion, I just want to point out that water activity is the energy of water in a system. And it's qualitative and inherent in the product itself because of the interactions that the water has. It's also a driving force. So it allows things to happen like microbial growth, moisture migration, and physical and chemical changes. For moisture content, it really is just the amount of water. It doesn't tell you what the water is going to do. It just tells you how much is in there. And it is not a driving force. So we're just talking about a qualitative amount, and that's all it's going to tell you. Water activity is critical for determining microbial growth, for maintaining the physical stability, like we talked about before, maintaining the texture. Use in product formulation, so we can produce a product that is what we desire and it will maintain that stability. Also chemical stability, we know we can also use that in our formulation, and we need it for predicting shelf life. All right, I want to thank you so much for joining us today, and I hope you found the webinar useful and informative. That concludes my prepared portion, and I will turn that back over to Brad.
Thanks a lot, Mary. We're a little bit over, but we do have, I think we can squeeze in a question or two. We've had a lot of great questions coming in, and we've been having our Meter Food team trying to answer a lot of those questions during the presentation. Let's see what we've got here, Mary. One here that I think we can do quickly, with water activity being, high water activity being somewhat, well, can be problematic for microbial growth. What are some things that you can do to decrease your water activity?
Yeah, certainly. You can use what are known as humectants, and humectants' function is to lower water activity. So you can have like adding sugar or salt, starches, glycerin, those kinds of things. Those can be added to your recipe essentially, and they will bind with the water. And when they do that, that reduces the energy of the water and reduces the water activity. But I should also point out that not all humectants work exactly the same effectiveness. So like a sugar and a salt works better than like a starch, which is a very long molecule. So hopefully we'll be able to have some future information specifically for humectants, but that's where you want to start, is looking at different humectants that you can use to try to lower that water activity in your product.
Okay. Let's see. I think we've got time for one more question here. And any and all of these questions, if your question has not been answered, we have these recorded, and Mary or somebody else from our Meter Food team will be getting back to you, getting in touch with you to fully answer your question there. So one last question here. Which is better, to measure the water activity in process or in the finished product?
Oh, good question. Actually, measuring the water activity during the process and at the end can be really useful. If you remember our caking and clumping issue that we had before, if that manufacturer had measured the water activity and the incoming raw ingredients, he would have known immediately that there was a potential problem with the caking and clumping. Also, I've seen a lot of seasonal fluctuation in raw ingredients, namely with like sugar, because of the way sugar's moisture content can be the same, but because of the structure of the sugar, the crystalline structure, moisture can kind of adhere on the outside. So the water activity will raise, excuse me. And so if that is put into a recipe or whatever, then that will increase the water activity and can also be an issue. So, but water activity can also be like a specification set for acceptance tolerances. You could say, okay, well, we can accept a water activity of our incoming raw ingredients in this range, knowing that when you put them together, that you're not going to have any problem with moisture migration and other stuff. You can also use water activity to measure process control. How well are you doing? Measure your consistency in your recipe before and after using the oven or the dryer, before packaging. All of these things make sure that the product will meet specs and have a desired shelf life. So you can do it the whole process, from raw incoming ingredients through your process, to make sure you're keeping a nice tight control on everything. And then also the end, that you're going to end up with a product that's going to have the desired qualities that you want and have the shelf life that you're wanting to have as well.
Awesome. Thank you, Mary. That's going to wrap it up for us today. Thank you again for joining us. We hope you enjoyed the discussion as much as we did. And thank you also again for all your great questions that you've got there. If you'd like more information on water activity or would like to talk with Mary further, please consider answering the short survey that will appear after this webinar. And also look for links to the recording and the slides in your email, and stay tuned for future Meter Food webinars. Have a great day.